Well, good morning and welcome everybody. Today is our final special lab day of the year. We are here for our aerodynamics, and I know that we are all ready to take off. We have the amazing Betsy Fortman here who is going to be leading our introduction. And I just want to remind everybody, we love student engagement. There will be opportunities with Slido and in the chat, so please do not hesitate to hop in there. But I'm going to stop speaking and let Betsy take it away.
Yes, you guys, thank you for inviting us into your classroom. I know it's like the end of the year, so the fact that you guys made time for this exciting STEM activity is really impressive. I know a lot of you already told us where you would like to fly. I love starting out this lab with this question because where you want to go? You've told me Australia, you've told me Switzerland, Utah. So how do you get there? These aircraft will take you there. Some have to go further than others, which means it has to be either lighter weight or have a lot more fuel to get you there. And so these are all the kind of trade-offs that we're going to be talking about today in our lab. So I'm super excited you all are already engaged. I do have two different displays up, so keep your answers coming and rolling in because I can see them right away here. All right, well, let's jump right into aerodynamics. One quick question I have for you now that you're all up and on Slido is which plane of these two do you think is going to go the fastest? So let me switch over. What do you think? Do you think it's plane A or do you think it's plane B? You guys are already rocking it. High fives to you. Yeah, feel free to type this in the chat too. If you don't have a cell phone to scan that or a different device, drop it in the chat. We got that for you too. And you're already rocking it. 100% of you are super smart today. Are you feeling it? So, yeah, if you look at these two planes, they're designed for something totally different. Just like we talked about, if you wanted to go to Paris or Australia or Greece, you want to get on a plane that's more streamlined, doesn't have to take as much luggage or potentially tanks or things like that that our military use. So, wonderful, wonderful job. You guys are already in the engineering mindset this morning. It's so cool. All right, you're probably wondering who is this crazy lady with this crazy background, right? I am Betsy Portman, as Monica introduced me, and I have been working in the space program since 1995, which sounds crazy long to me. I've had various different experiences, all from NASA over to the Commercial Crew Program. So I'll just give you a quick rundown of like how I started. I started off very similar to you guys. I remember being just curious about everything. I used to love to take things apart. So much so that you guys, I took apart my mom's car door when she left me and my sister in the car, and I could not shut it. And I ended up having to like hold the car door, or she had to hold the car door, and I was like told to get to the other side and drive us home like this. It was not good. But I now know that's called reverse engineering when you study something and then take it apart to learn how it works so that you could build something either like or maybe even optimize it to be better. I did go to Purdue University where I got my bachelor's of science in aerospace engineering. And then from there, I started working with NASA out at Langley Research Center as a co-op. So I was working on the F-18. And when I first got there, we were putting sensors underneath the F-18 and then putting it in a wind tunnel and testing it. And I remember thinking, I totally understand why my professors made me learn all these crazy long equations about how air flows over the sides of the wing, which I thought was like, why are we learning this, right? And we have computers that do that. Since then, I graduated college and then went down to Houston, where I joined NASA's Johnson Space Center and I worked on a whole variety of different spacecraft. You can see in the upper left the International Space Station. I was training our astronauts to take them up to the International Space Station on the guidance, navigation, and control system. So this is like how we orient our spacecraft with respect to the stars, how we do reboosts and things like that. And then when we come in and do dockings and undockings and all of those good things, I did work overseas with our astronauts over in something called Star City, Russia. And so Star City is, well, that's the translation. So that's where their cosmonaut training center is. And so when our astronauts would train on the Russian parts of the vehicle, as well as the Russian Soyuz, it was kind of my job to go with them and help learn the systems and then help make sure our astronauts had all the materials they needed and understood the systems and were prepared for their tests. Because guess what, you guys? They're just like you. Instead of going to like geometry and math class and science and English, they're going to the power system, the computer system, and the docking system. And then they have to take tests just like you to make sure that they're ready to fly as well. Down here, you can see the Orion vehicle. This is the one going to the moon and Mars. And then over here, we have SpaceX and Boeing. So I was helping our astronaut office as their chief engineer, preparing for what we call exploration or commercial crew program, where we were making sure we had the requirements and everything set for the Boeing and SpaceX vehicles. And then over here on the right, my latest endeavor, I had been working with Sofix Synergistics as a consultant for Opsium, helping to get their space station up as well. So that's me in a really quick nutshell, but we're here for you guys today, so I can't wait to jump right in. One of your questions came from Stephen Moody Complex, and you guys asked, what career options are there in this field? Well, you can see on my screen here, I had a variety of options, whether it was just working on one subsystem, whether it was working on a launch vehicle or the vehicle that the crew would take, or just helping to define the requirements that would take the next cruise up. So there's tons that you can do, and it doesn't necessarily just have to be in an engineering capacity. Like you may find that you are super good at testing something or designing something, or you want to be the person handling the PR for how something is launched. So there's so many aspects to engineering, that if you are interested in something, I promise you, you can find a niche that would fit you just well. So wonderful question out there. Thanks so much for asking that. All right, as you know, all of our Engineering Tomorrow labs are created by a team of amazing engineers and college interns. You can see up on the screen, Joanna and Edgar helped to create this particular lab. And on the bottom right, you can see we also had a redevelopment of this where we added a couple extensions for you as well. All right, so I am ready for you guys to think like engineers. So as an engineer, we have lots and lots of considerations to think about. I am curious, if you got to fly a helicopter on Mars, what would you need to think about? What would be different? I'm going to go ahead and throw this one up on the screen. I'm curious. What might be different in Mars versus Earth that you would have to think about? You know, if you guys have seen this particular um, spacecraft. It's actually a helicopter. It's on Mars. It's called Ingenuity. It was designed for 5 flights, a mere 5. Guess what? It had 72 flights the last I had heard. And so I just find it incredible that this particular aircraft is up on another planet flying. So if you guys are thinking atmosphere, you're dead on. High five to you if that's you. Or maybe you're thinking like, how do I power it? Right? So we can't just have batteries and then let the batteries die. We have to be able to recharge it. So some of the things like renewable energy, being able to charge this particular aircraft so that it can fly. And then the rotors, of course, would also have to be working on another planet with less dense atmosphere and all of those good things. We're going to study a little more about some of the specifics here, but I did want to play this quick snippet for you because I just think it's so incredible. What an amazing engineering feat. So let's listen to this real quick.
First helicopter to fly on another planet.
The challenges are many. Ingenuity first must disconnect from the belly of Perseverance. It's a multi-step process already underway. This picture taken Sunday of the detached debris shield. Once Ingenuity is detached, it has 25 hours to gain enough charge from the sun to independently survive a Martian night. Then there's the challenge of actual flight. Mars' atmosphere is only 1% of Earth's atmosphere, so engineers had to develop a special twin rotor system that could provide the necessary lift to get airborne. Also in flight, the helicopter has to control itself, making 500 tiny adjustments every second. Bob Balaram is the chief engineer for the Mars Ingenuity project. He says it's every bit the Wright brothers moment. It's just on Mars.
All right, you guys, is that not incredible or what? I just love that snippet. And also, one of you already put in the Slido about things to think about on another planet. Gravity. You are 100% correct. If that is you in your class, high five to you. Yes, gravity is different because Mars is a different planet, right? And so it has a different pull into the actual planet itself with gravity. So having to counteract different forces on one planet versus another. Great, great job, you guys. All right, so today's design challenge, you will be figuring out the different forces on an aircraft, and you will be designing your own aircraft. In fact, you're going to be designing at least 3, if not 4, different aircraft today and doing several different tests. So I want to kind of show this to you real quickly. But before we do, I wanted to hit Evansville High School had sent in, sorry, Evansville and Queens High School had sent in a question. How does the aerodynamics of a plane relate to automobiles and sports cars? Wow, this is such a great question. So you can see here, this is a wind tunnel. And you might be thinking, what is a wind tunnel, right? So it's this giant, basically, tunnel that you push air through. And that will simulate flight or, in this case, driving a car. And you can see here, they've induced a little bit of like colored smoke, it looks like, so that you could actually see the streams of air and you can tell like how it's hitting that car, right? The same is true for aircraft. We do the very same thing in the tunnels. When I first was a co-op, I was working at NASA Langley, and I was telling you that we were working in what was called a transonic dynamics wind tunnel. And we were testing very similarly like this. There's a control room that would be out here on your right, where the engineers are sitting and monitoring the data as the wind tunnel is blowing the air through the tunnel itself. So this is such a great question. The next one that goes along with this is, how do you test experimental aircraft? So this is exactly how we test it. So whether it's a car, whether it's an aircraft, this is the same setup that you would be doing. So Alamo, now, awesome questions. You guys keep them rolling to us. All right. So what is going to be your job today? I'm going to teach you a little bit about aircraft and how we control them, but I want you to know where you're heading with this. So what you're going to be doing is, on the left, you're going to be actually taking 3 different aircraft that you get to choose which ones you want. And raise your hands here. Has anyone done March Madness before? So probably out there, yeah? Okay, so it's like that. You're going to find the winner of these 3 that you create, and you're going to test it for flight time as well as distance. And you're going to see like which plane is doing the best. From that, you're going to choose the winner. And you're going to add some control surfaces. Maybe you're going to put some flaps to the back, maybe elevators and things like that. Maybe some winglets out here on the sides. And we'll talk what all of those terms mean here in just a second. After you get your control surfaces, you can test this as well. See which control surfaces are working for you. And then on the far right, you're also going to, if you have the time, adjust it for what we call ballast, which is like additional weight in different areas. And we're going to use paper clips to do that. So keep this in mind as you start learning some more about aerodynamics. Okay, so how does a plane stay in the air? You might have thought about this before. So lots of different forces are acting on your aircraft. You probably have a worksheet. If you have a worksheet, I recommend pulling it out, because this video here is going to give you some of your answers, especially on that first page to the bottom, there's a diagram. So let's go ahead and listen to this video real quick. And it's going to explain about lift, drag, thrust, and gravity. Here we go.
Airplanes stay in the air because of one simple fact: there is no net force on them. And with no net force, an object at rest stays at rest, and an object in motion stays that way, even if it's in midair 10 kilometers above the Earth's surface. Now, of course, it's not like there aren't forces acting on the airplane. Gravity pulls down on the plane itself, plus all of the people and baggage inside, and every single air molecule that's shot through the engines or collides with the fuselage or wings pushes on the plane as well. But if all of these forces are balanced, in particular if the air molecules push the plane up enough to counteract gravity, then the plane stays up. Getting air molecules to push the plane up is the crucial part of flying, and planes do this by making sure the undersides of the wings crash into more air molecules more violently than the upper sides. When a plane is parked on the ground, air molecules bounce off of the top and bottom of the wings in roughly equal amounts, or with equal pressure, and no lift. But in motion, the curved shape of the wings and their slightly inclined angle means that the bottoms smash into more air molecules than before, and smash harder into those molecules, so the pressure on the bottom of the wing goes up. In addition, fewer air molecules now strike the top of the wing, and those that do strike it less forcefully, partly because it's being shielded by its own forward motion, the way running into the rain keeps your back drier, and partly because a curving stream of air has lower pressure on the inside of the curve since the molecules get thrown centripetally to the outside. But whatever the reasons, the pressure on the top of the wing goes down. So low pressure or less downward force on the top, plus high pressure or more upward force on the bottom, and the plane has lift. And if the force imbalance is big enough, it can lift the plane up into the air against gravity. Now, all this crashing into air molecules to lift the plane also pushes to slow the plane down, which it would if not for engines. Engines also push air, in this case backwards.
All right, so you heard a whole lot about lift and drag and thrust and gravity. What I wanted to mention here, so again, on your shortened worksheet, if you're using that, otherwise if you're using the long one, that's fine too, you'll notice that we have lift is the one going up. If we have higher lift, it's going to take us up into the air, higher than the weight of the plane. So that's really important. If we want to take off and go to Disney World or somewhere really cool, like Australia, like you were saying, we need to make sure that vector is more than the weight of the plane. However, there are times when we want to come down, right? So a lot of times we will adjust that angle of attack to help us start coming down and have less lift so that we start coming down back to earth and things like that. You can see here, if any of you are ball players, you're probably very familiar with putting that spin on a ball as it is flying. If you have a curved ball or something like that, if you put no curve on it and it's just flying straight at the batter or someone like this, you can see that the equal forces, just let it go straight in for a nice strike. Over here on the left, I don't know about you guys, but this picture doesn't really help me very much. So let me explain a little bit what you're looking at. If you cut this wing right here, right down that line, and looked at the plane from that angle, if I were to pull this out, that is called an airfoil. And so a lot of times you'll see aircraft shown with the flow over that wing right there, which is kind of that cross section that you're looking at. Again, we're looking at the fact that it has this slight angle of attack, as well as you'll see that airflow is hitting the bottom more, giving it more upward force. So that's kind of what you want to think about as you're creating your plane. Like, how do I get more lift? And guess what? Lift is going to be affected by how your plane is built, right? So do I want a plane that has straight set of wings? Do I want a plane that's swept back? Kind of like this, kind of like some of our aircraft for the military and things like that. So think about the surface that's going to provide that lift, which is your wings. And then also, how heavy is your plane going to be? How many pieces of paper are you going to use in order to create it? In this instance, we're going to try to keep the weight as low as possible. I'm going to go ahead and show you one real quick. You're welcome to make one with me, where we're actually going to make a lifting wing, and you can check out how the aerodynamics are playing together. So let me switch over real quick to my other camera, pull out a piece of paper while I'm doing this, and join me as we make our lifting body here. All right, are you seeing my happy face, hopefully? Awesome. All right, so here we go. We're gonna go ahead and make a glider, which is basically just a big lifting wing surface. So we're gonna take the corner of the one side of paper and fold it down. Now you'll notice I have different patterns on both sides to help differentiate with you all. All right, so here we go. I'm gonna take it and go all the way across. And here, as we do this, we want to make sure we have some nice, dirty lines so that we're making sure that we're getting this really symmetric. we're going to take the opposite corner and fold it over to the other side. It's going to look a little bit like a house, right? So here you go. You got that going on. Okay, everybody following? Now I'm going to go ahead and fold this in half. Hopefully I'm not going too fast. If I am going too fast, you guys have the video replay. You can watch this again, okay? So don't stress. Fold the one side down just a little bit. Notice I've made a body here. This is what we would call the fuselage of a plane. The fuselage is kind of where the people sit kind of thing. And then I'm also going to fold the other side and make it very symmetric. I want you to be thinking, why would I want it symmetrical? Okay, think about that. Why does it need to be symmetric? Why are all our planes and cars and rockets all kind of similar? All right, so now we have a really nice glider, right? One other thing I like to do is to kind of bend this down one here, kind of give you the ability to push back that center of mass. And again, just refolding those same lines. All right, you should have something that looks like a nice lifting body here. Just like that. All right, we're gonna test this one out. And I want you to go ahead and test yours as well. Oh, I'm hearing that you may be seeing a lot of slides still, so let me make myself bigger. Again, this is kind of what you're looking for. I'll undo it real quick just to go one time through it all over again. Ready? Here we go. Fold down one corner, all the way to the opposite side. Make a nice big triangle on that side. Fold the opposite corner down, making sure you got nice lines. At this point, you can go ahead and pull that nose backward to move that center of mass more towards the back. That's going to help make it more stable for you. Fold down the center line. Now it should look a little bit like a trapezoid or a half a trapezoid, I guess you call it. And then we're going to go ahead and make the fuselage, which is where the people sit basically, or the body of your plane. So now you should have a really nice glider that you can test out in your class. If you go ahead and toss it, feel free to turn your cameras on if you are ready for that step and see how far it goes. From here, we're going to make some adjustments. So let me go back to our slides, okay? Going back to our slides here. We're going to make some adjustments. How can we make this lighter weight? Maybe you're going to consider making some holes in it to take out some of that structure. Maybe you're going to add some control surfaces. So maybe some elevators or some flaps. One other thing is a winglet. So winglets, let me show you another one. Winglets are when there's like the side of the wing that goes up. All of these are different control surfaces. And so when you get to making your plane, you're going to choose which control surfaces work best for you. I'm going to go ahead and switch my camera back to me 1 second. If you have tested any of your lifting body gliders out there, I would love to see it. Otherwise, we'll wait as we get to testing a little bit later in the day to check some of those out as well. All right, I talked about weight. One thing to know about, there are aircraft out there that have switched to like carbon fiber composites. You guys, guess what? Those have reduced the mass of the vehicle so that they can actually fly so much further. And guess what? It replaced 1,200 sheets of aluminum and 40,000 rivets just by doing the fuselage with this carbon fiber. Isn't that amazing? Just imagine the savings there. So this is one of the reasons the Boeing Dreamliner can go further than a lot of the other aircraft of its size. I think that's just so cool. Thrust. You guys saw in the video about thrust. A lot of times you will notice that thrust is coming from what we would call an engine, right? So the back here in an aircraft is giving you that thrust backwards to push you forward. As you all know, every action has an equal and opposite reaction. In our case, we don't have engines on our particular aircraft that we're working on today. So what we are going to consider the thrust is our arm movement. Hint, hint, this is in your workbook. If you're following along, you will have an answer. So in our case, our thrust is going to be coming from our arm, and actually having the ability to throw it at the same angle is really important, as well as to give the same like thrust force. So you're going to want to make sure that you're being pretty consistent as you provide that thrust forward. On the screen, you can see what typical engines look like and that provide our thrust: the turbojet, the turbofan, the turboprop, that you can see up on the screen here. Drag. You guys, as we started this class today, already told me which plane you thought was going to go faster. Obviously, air is going to flow over these aircraft differently, right? I would imagine this particular plane is going to go way faster than the plane down here. And you can just imagine that streamlinedness. So when you make your aircraft, think about how to make it more streamlined in order to reduce the drag. That will be super important. Okay, here we go. And one of you asked, how does this all relate to cars, right? So if you imagine the aircraft have to worry about the different streamlinedness and, taking down that drag, the same is true with cars. Like, I bet you're already figuring out this big truck is gonna go a lot slower than this pretty cool car here. If you know who this car is, drop it in the chat. I do not, but I thought it was a pretty nice looking design there. So can you make your aircraft look as streamlined as that particular car? That's so cool. But keep in mind, aircraft also need that lift factor. So you're going to have some wings that go out from your fuselage as well. All right, what is the biggest factor in lowering aerodynamics resistive forces? New Rochelle, you guys asked such a great question. So if this was just a question, what is the biggest factor? I think I probably would have just, thought about lift and thrust. But because you said lowering aerodynamic resistive forces, which to me means drag, I feel like the streamlining is probably the most important factor to reduce that drag. So such a great question. I love it. All right, you might be thinking about, how does your plane steer? So in aircraft terminology, we always think about roll. If you think about barrel rolls, it's just going along that line and rotating. Roll, pitch. Pitch is going up and down. So like when we're taking off, we're pitching up. When we're trying to land, we're probably pitching down and then pulling up just at the end there. And then yaw is that movement that kind of goes left and right. And this is true with aircraft, but as well as spacecraft, you guys. We use the very same terminology. And we use something called Euler sequences that go in a particular order for those. If you give an attitude of yaw, pitch, and roll, or roll, pitch, and yaw. On the screen, you see some of those control surfaces I was talking to you about. So think about what ones you want to enter into your design. And as you do this, one of the most important things is, as you're testing 3 different planes and you start putting in these control surfaces, what ones do you want to use? And when you use them, change only one at a time and test it one at a time. That way you can be sure like which one is actually helping and which one isn't, so that you don't have this like mixed information coming to you. So I am curious, what one are you guys going to try out? Are you going to do the elevators? Are you going to do the vertical stabilizers, horizontal stabilizers, the winglets? I really like the winglets. One tip for your winglets: don't make them too high, because remember, you still need a big lifting surface. So make sure, if you're making those winglets, to make them kind of smaller towards the edge there. Oh, look at you, leading edge flaps. Way to go. High five to you. I cannot wait to see your designs. All right, just to reiterate where we are going to be doing the planes. First, you're going to use the paper that was sent to you, or you can use your notebook paper, whatever you feel comfortable with. We did send you a propeller as well that you can use to rotate and then provide some thrust with that as well. And some different straws. I use the straws as what we call stringers. Let me show you real quick. To help stabilize my wings when I use the propeller plane. So if that's you, just some real quick tips there. Again, you will have in your workbook a QR code, or if you're in the extended workbook, you will have links that will take you out to various websites and show you how to make different planes. Choose your favorite. Look at the designs. Now that you know how to control airplanes, now you know the forces on airplanes, which of these do you think is going to work the best? And create those 3. After you do those 3, test those 3. In your workbook, there will be a table that you'll be filling out for which plane goes the furthest and which plane stays up the longest. Pick the winner, just like in March Madness, and then start iterating some control surfaces. Again, it sounded like some of you are interested in making the leading edge flaps, so try those out. Let us know how that goes. And then if you get further than that, you will then go out and adjust your center of gravity by adding paper clips to different parts of your aircraft to see if you can move the center of gravity back to give you a little more lift and hopefully get your plane to go further and longer. I can't wait to see what y'all do. Thank you so much. Monica, I'm going to go ahead and turn it back over to you.
Well, I want to give Betsy a round of applause for a fantastic introduction. I think everybody is ready to open up those kits and get to the building. We are going to open up our breakout rooms now, where we have our college mentors along with our ET staff engineers who will be in there to assist you with your design. Additionally, I'm